Welcome back to our lecture series on material science and metallurgy subject. In today's lecture, we'll talk about ferrous alloys, under which we have been discussing on the cast iron. In today's lecture, we talk about the ductile iron. It is also called as spheroidal graphite iron or SG iron. We will see why it is called spheroidal graphite or spheroidal graphite iron. In today's lecture, we talk about ductile iron in terms of their composition, their microstructure, their properties and their limitations, and some of the applications of this material. We'll discuss about it. And towards the end, we summarize and discuss the key takeaways from the lecture. In the previous class, we talked about grey cast iron. If you look at the microstructure, if you recall the microstructure of grey cast iron, which comprises of graphite flakes, and we have discussed that graphite flakes will define the properties of the material. That includes high compressive strength and low tensile strength, good damping, vibration damping characteristics, and things like that. And if you see the ductile cast iron here in today's lecture, so it is also known as nodular cast iron and also nodular iron, nodular cast iron, nodular iron, ductile iron or ductile cast iron, or spheroidal graphite cast iron or spheroidal graphite iron. All these are belongs to the ductile cast iron. It is a high strength cast iron material which is offering very high strength with spherical graphite nodules. These graphite nodules, graphite present in this material in the nodular form, they are in spherical in shape. That's why these cast irons are called as nodular cast iron or nodular iron, because the presence of graphite in the nodular shape, nodular form, and these nodules are spherical in nature, and so it's also called as spherical graphite. Graphite is present in the spherical shape. That's why it is called spherical graphite cast iron or spheroidal graphite iron. So what is causing this spherical graphite nodular shape? And in the case of graphite, that is in the grey cast iron, graphite is present in the form of flakes, like a cornflakes. But in this case, it is present in the form of spherical. So it's in the nodular structure or spherical. That is due to the addition of these alloying elements, that is magnesium and cerium, because of the treatment of this cast iron with magnesium and cerium alloying elements. This graphite will take the nodular structure, nodular shape. So this ductile iron combines the good properties of graphite iron, that is a grey iron, grey cast iron. Grey cast iron, we have seen that it is having excellent castability because of the good fluidity characteristics and also low melting points. So it basically, ductile iron basically combines the good castability of grey iron and also the mechanical properties of steel. We are known that steel is having excellent mechanical properties, because of which it has been widely used in most of the engineering applications, particularly in construction sector. So this ductile cast iron combines these two properties, the good mechanical properties of steel and good castability of grey iron. It combines both, and you get this ductile cast iron. And it is developed in 1948, which has revolutionized the entire cast iron applications. This invention has revolutionized the cast iron applications, which is primarily developed in 1948. If you look at the composition, element-wise composition, carbon is present up to in the range of 3 to 4%. Carbon is present which is higher than the steel but lower than the gray iron. So gray iron can go up to 4.5 as well. So, but it is close to gray iron, but marginally lower than the gray iron, but it is higher than the steel. Silicon is also present to a larger extent, that is 1.8 to 2.8 percentage. And in the previous lectures, we have seen that silicon primarily promotes the graphite formation. It promotes the decomposition reaction of FeC3, FeC3 decomposing into iron and the carbon. So this carbon is present in the form of graphite. So this reaction has been promoted by the silicon, right? And it is also having the magnesium. Magnesium is very fraction, very less amount only, 0.03 to 0.006 percentage of magnesium has been added, and it is critical for graphite spheroidization. Okay, spheroidization. Sorry, graphite spheroidization, the formation of graphite in spherical shape, spherical form, that is caused by the addition of magnesium and cerium. Cerium are the rare earth material, so which is backing up the nodularizing agent. It is a backup nodularizing agent. When when performance of magnesium is in shortfall, then the cerium will act as a backup agent for nodularizing the graphite. In addition to that, we also have other impurities, other materials, like it contains low sulfur and low phosphorus, which is 0. Less than 0.02 percentage and less than 0.1 percentage respectively. So low sulfur essential for magnesium to work effectively, and phosphorus will avoid the embrittlement of the material. So this is the comprehensive composition of ductile iron. It consists of carbon, silicon. Silicon is required for the graphite, and magnesium and cerium is for nodularizing or spheroidizing the graphite. And to effectively make sure that this sulfur is effectively working, so that is taken care by the sulfur, and whereas the phosphorus is which is added to avoid the embrittlement of the material. If you look at the microstructure, so these are the graphite that is present in the spherical shape or in the nodular structure. So these are the graphite. In this case, graphite exists in the form of nodules, which are basically spherical particles. So which is surrounded by alpha ferrite or perlitic matrix. So if it is surrounded by the ferritic matrix option, three options are there for us. So if it is surrounded by the ferritic matrix, then it is called as a ferritic ductile cast iron, which offers very high ductility, and ferritic is weak in nature, and so it is lower in strength, relatively lower in strength. And you have an option to have paralytic matrix, which is offering good strength as well as lower ductility. You can also have Aus-tempered matrix, ADI, Aus-tempered matrix, Aus-tempered ductile iron, ADI, Aus-tempered ductile iron, which is having a binetic structure, which offers ultra high strength for the ductile cast iron. As we have seen, ductile iron it's basically having the properties of good castability that is coming from gray iron, and it is having properties, it produces properties which are comparable with the steel. So that is coming from these paralytic or Aus-tempered matrix combination. Since graphite is formed in the shape of spherical particles, and there will be no stress concentration region. Unlike the flakes, in the case of gray cast iron, these graphite is present in the form of flakes, which are the root cause for the stress concentration region and low tensile strength. And in this particular case, graphite is present in nodular shape or spherical particles, spherical shape, and so there is no stress concentration region. So nodules act like a ball bearing under the external, and when they are subjected to the external loading, which basically reduces the crack propagation. So it arrests the crack propagation basically, ball bearing, which acts like a ball bearing graphite. If you look at the properties, these castings are very strong and much more ductile than the gray iron. Ductile iron has excellent mechanical characteristics, that is almost approaching the characteristics of the steel in terms of its strength and other properties. Ductile iron owes its remarkable mechanical properties to the spheroidal shape of the graphite in terms of their tensile strength, impact resistance, high elastic limits, good elongation. So all these are primarily coming from your spherical nature of the graphite. So ductile iron owes remarkable mechanical properties that is primarily coming from the spheroidal shape of the graphite. So what kind of properties or what are the properties that we are talking about? It is the tensile strength, impact resistance, then elastic limit, higher elastic limit, and good elongation. That is all coming from your spheroidal shape of the graphite. So these properties further they can be controlled by the chemical analysis as well as the heat treatment of the metal matrix. So further they can be improved if they are brought into the Ars tempered form where it gets a magnetic structure and offers the ultra high strength to the material. And through some chemical analysis also you can further it can be enhanced. So ductile iron maintains the traditional qualities of cast irons resulting from high carbon content. So, in addition to the shape, because due to the shape of spheroidal shape of the graphite, it offers excellent tensile strength, impact resistance, elastic limit, high elastic limit, and other one more property here. That is a good elongation. That is coming from your primarily coming from the spheroidal shape of the graphite. In addition to that, by default it is basically it is a cast iron. So whatever cast iron is having in general characteristics, those all those properties are also applicable for these ductile iron. That includes good compression strength and good castability due to high fluidity and low melting temperatures, and very good abrasion resistance because of good or good hardness, and it is also missionability also. These components are missionable, though it is hard, but they are missionable. It offers excellent fatigue strength also. It is when they are subjected to cyclic loading, it offers a very good resistance. These all these are the qualities of general qualities of cast iron. So these are also applicable for your ductile iron. So it is overall a good comprehensive material which is having uh, a good trade-off between all the properties. The strength of the steel with the castability of iron. In short, we can give this particular title to the ductile iron. The strength of the steel with castability of iron. However, they also have certain limitations, that is higher cost, particularly the magnesium treatment adds the expense, because magnesium is the one which promotes the spheroidization of the graphite. So this magnesium treatment adds up the expenses, and its shrinkage porosity risk is there. When it is shrinking, there is a chance that there is a chance that voids can form in the material. So that is another risk which we are talking about. So this requires careful casting design. So if you see the applications in the automotive industry, they find applications in the crankshafts, and differential housing is also manufactured out of ductile iron because of their excellent strength. And in pipes and tubing also, our regular water and lines, sewage pipelines, they are made out of these ductile cast iron because of their excellent corrosion resistance. One more important property. And in the industrial sector, they are being applicable for manufacturing the gears, rollers, and heavy duty couplings also manufactured out of this ductile iron. Then in the wind energy sector, Mostly their blades are manufactured out of composite materials, glass fiber reinforced composites are composite materials, but their hub castings, no, they are manufactured from ductile casting. They offer high strength and fatigue resistance. Cyclic loading is very very important in the wind energy. So it is 70% of the ductile iron is being used in the water infrastructure globally. So if you see the applications, overall applications, 70% of the ductile iron finds their applications in water infrastructure globally. So if you summarize what we have discussed, graphite is present in nodular form, which enables the ductility for the material as well as strength. It has having good elongation characteristics along with the excellent strength. Magnesium treatment is the heart of the ductile iron production because magnesium um, is uh, is the one which promotes the spheroidization of the graphite. However, this magnesium can fade. That remains a challenge. So magnesium under high temperatures, it can fade out. So that remains a challenge for us. So that's why its overall expense is also little higher. It's one of the limitations what we have discussed. ADI, Austempered ductile iron pushes the performance to the steel-like levels. So it almost offers strength close to the steel. So from sewage pipes to the SUV axles, ductile iron does it everything. So we can give this code from the sewage pipes to SUV axles. This ductile iron finds their applications. So for this lecture content, I have followed these textbooks. To a question to ponder your brains, I'll leave it with this question, this lecture. Why can't we use ductile iron for high temperature applications, which is above 500 degrees centigrade? Why can't we use ductile iron for high temperature applications? A hint is given here: graphite coarsening plus matrix instability. Matrix, we have discussed what are the matrix options that we have, like ferritic, paralytic, and austempered matrix combinations are there, and also graphite coarsening is also we have discussed in their limitation, graphite fading out or magnesium fading out, we have discussed this. So the answer is given in the hint itself. So once you get the answer, please respond in the chat. So with that, I'll close this lecture for today. Next lecture we talk about white cast iron. Thank you.